Well, good evening, ladies and gentlemen. Welcome to the Astronomy Society of Edinburgh. And tonight's talk on cold dark matter. Is it cold? Is it dark? Or is it matter? A few things to talk about. Got some news that's coming soon. And then the presentation from Dr. Julian Onions, University of Nottingham. So really important for everyone who are members. The current ASE Council, including some of the folks on this call, stand down at the 6th of June meeting. Nominations were called for a few weeks ago, and nominations are now in. So it'd be really useful if you could attend in person. I know everybody can't, at the Augustine United Church in Edinburgh. If not, there'll be online instructions for joining. And the papers will be emailed out to you this week. So coming along in the near future, we've got 4 centuries of clue about how the sun gets its spots. Well, I'm really interested in that because when we do our open days at the Royal Observatory, we always get about 1,800 questions about where the sunspots come from. And then people say, well, prove it. And that's quite difficult, actually, you know. But so that'll be good. Then we've got our normal internal imaging observing group. And then supernova and the search for dark energy. We were just talking about dark energy and the fact that, you know, it's more of a mystery or an unknown than dark matter. Then we have a lengthy summer break, July and August. Although, you know, as Mark says, don't stop taking the pictures, don't stop studying. Just there's lots of things to do, even though it's not particularly dark in Scotland. And then we kick off again in the autumn with the liquid mirror telescopes, which is a really interesting subject. I just read something on that recently. It's from Professor Brad Gibson. So looking forward to that. And I believe, Nigel, we have talks booked up for most of the rest of the year. Is that correct?
Yeah, we still have a couple of slots to fill for the latter part of the year into November, December. But yes, we're pretty good. I hope to get everything filled up by the end of the summer break.
Okay, that's great. Okay, so I think it's over to you, Julian. I shall stop sharing and let you take control.
Okay. Okay, I think that should be the one I was hoping to share. Can you all see that?
We can do.
Yeah.
And audio is coming over okay, is it?
Yes, it is. Yes.
Audio's fine.
Fantastic. Right. I'll move on with the talk then. So, yeah, the question is cold dark matter. Is it cold, dark, or matter? So I'm going to talk to you about cold dark matter. And it's a bit of almost a shaggy dog story in that there's no real conclusion to it. So you could tune out now and not be less wise. So, but it's in 3 parts. So the first part is, why do we believe it exists? So, you know, what is the evidence that there is something around like dark matter? And, you know, why do we hang on to this fact? Secondly, well, okay, if I can convince you of that, which I may not, what could it possibly be? What have we got left in the bag of bits and pieces that make up the universe that perhaps it could be? And thirdly, how can we go about finding it if that is the case? What methods do we have? So I think a good description of this talk is something that Enrico Fermi was supposedly said that, before I came here, I was confused about the subject. Having listened to your lecture, I'm still confused, but on a higher level. So that's kind of what I'm hoping to achieve here, that you're all going to be confused, but it's going to be a sort of more informed confusion than it was before. So this is what we believe the universe is made up of at the moment. It's about 5% of the stuff that we've been studying for the last 400 years, which is atoms and particles that we know. Dark matter is somewhere between 23 to 27%, depending on which experiment you follow. And dark energy makes up the rest, somewhere between 68 and 72%. So I'm not going to say much about dark energy, but that's good because you've got a talk coming up on that. So possibly one of the usual reactions to this is, what, really? I mean, you're just making stuff up, surely, aren't you? And that maybe it's something a bit like this, that we've got an accountancy problem here, that 1 and 1 is 3. Well, that's not the case, is it? But, let's try adding a dark number, and suddenly it is, and that's maybe what we're doing here. We're filling in from the rest of the universe. And I also found this cartoon recently, which I really liked about it, so you can read that. But the synopsis is that it does appear from the outset that we're just making stuff up, and that is probably a reasonable reading of the runes. But although this is not the way you should do science at all, we have been here before. We've made up stuff in an obscure corner of physics, and it's turned out to be right. Now, when they made it up before, there has been quite a lot of evidence behind it. The first case was Wolfgang Pauli, who decided that with certain reactions which were not behaving themselves and not obeying laws like the conservation of energy, conservation of momentum, that we either had to abandon all those laws or we could assume perhaps there was something else. So he proposed this particle called the neutrino in 1930. He was a bit shamefaced about it and said, I've done a terrible thing. This is a particle that cannot be detected. But if we just believe it's there, we can get back our widely held beliefs about conservation laws. So he proposed that, didn't really think it could be detected because its very presence was that it should be pretty much undetectable. But luckily, not everybody followed that, and in 1956 there was indeed detections of neutrinos. That led to a few other issues, but we'll skip over those for now. Also, something you're probably very familiar with, being in Edinburgh, is Peter Higgs, who proposed a Higgs boson in 1964. And it took a while, but finally detected in 2012 in time for him to get the Nobel Prize. So, yeah, I mean, there was quite good reasons why both of these people made up this new particles, and they were proved right in the end. So dark matter, well, sort of 1932 was the first mentions of dark matter, or first inklings. And so if you want to leave now, we're still waiting to actually detect it in a meaningful way. So that's where we are. Just going to veer slightly off to cosmology, because it really underpins all the cosmology, which is the study of the universe, how the universe begins and ends, and etc. So the underpinning theory at the moment is called lambda CDM. So that's the lambda, Greek lambda, and CDM. So that's our current model of the universe. This lambda is kind of the placeholder for dark energy, the repulsive force that's pushing stuff apart. And CDM is the cold dark matter, which I'm going to talk about. So yeah, really don't know very much about the dark energy term, this lambda, but then not very many people do either. So it's something that kind of underpins anything that you do with cosmology. So you can see everybody kind of starts from lambda CDM unless you're straying outside. So the lambda term kind of comes from, or at least appears in Einstein's field equations. So there's a bit here about how space curves, and the rest of it tells you how matter behaves. And this is almost my complete summary of dark energy. You'll get a much better one from Professor Hook, I should think. But there's three possible scenarios of the universe, how it will end up. There's a big crunch where the universe stops expanding and comes back into itself in what's called a big crunch. It's a very nice, clean model, but one that seems to be wrong at the moment. Nobody seems to have any evidence that the universe is going to collapse in on itself at the moment. Indefinite expansion is kind of where we are at the moment. That seems the most logical because that seems to be what's happening. There is a more extreme version called the Big Rip, where everything gets ripped apart, from galaxies to planets to you and me and atoms themselves. It was thought that maybe dark energy could be something called vacuum energy, but that's not the case, or at least it's very hard, because if you do the calculations, it's wrong by this factor, which is one of the biggest errors we've ever had in physics. Even astronomers, who are kind of fairly sloppy with errors quite a lot of the time, that's pretty big even for them. So that's all I really know about dark energy. So we'll get back to the dark matter. So the cold bit, that refers to the speed of the particles. So cold means it's moving relatively slowly. It could be moving at thousands of kilometers an hour or kilometers a second even, but it's not going at the speed of light. So there is another older theory called hot dark matter. In that case, the particles were moving at the speed of light. So this really just distinguishes them between hot dark matter and cold dark matter. Hot dark matter was kind of disproved in about the 1980s, or at least it was shown to not be a realistic theory. The dark is rather a poor term. It means it can't be seen. And in fact, our understanding is that it has no interaction with light whatsoever. So light and dark matter just don't see each other. So there is no way you can actually light it up. And the matter bit probably becomes from considering it as particles rather than something like a radiation field or something like that. So that's kind of where cold dark matter comes from. And we're not entirely sure about any of those three at this point. The other thing about it is with the current theories, it needed to be there at the beginning of the universe too. So this is kind of what the universe was consisted of at the beginning. Dark energy was absent at the very beginning. It's kind of a property of space. So as space expands, you get more and more dark energy. So that's how it was. These are the latest results from what's the probe? I've gone with the probe's name, but this is our best constraints on it. So it's about 68% dark energy, 20%, 27% dark matter, and the rest is stuff we're more familiar with. So let's start with the history. How did we get here, and why do we still think it's the case? The very first person to come up with anything slightly weird was Jan Oort, an astronomer. I think he was Dutch. He probably recognize him from the Oort cloud, which he also gave his name to. So in 1932, he was working on trying to position exactly where the sun was within the Milky Way, and he was looking at the motions of stars around the galaxy inside the orbit of the sun, and said he got a very good result for this. But one of the side effects of this was that he only saw really about a third of the stars needed to hold the sun in its orbit. There really needed to be a lot more mass within the orbit of the sun to hold it there. The sun is held in orbit around the galaxy by the gravity of all the stars interior to it. And this was, he really couldn't find those. So he flagged it up as an issue and said, well, telescopes will get better, we'll get better things, we'll probably find it all. Then Fritz Zwicky, who was certainly quite a character, he came up with a kind of a brilliant new theory in astronomy every couple of years, and most of them have turned out to be correct. Anyway, this was his contribution in 1933. He was looking at the Coma cluster of galaxies, which you can see here, and he was trying to weigh them, work out how much mass was in them. he got a reasonable estimate of how far away they were, and he had two ways of measuring the total mass of all the galaxies in there. You can look at the amount of light coming from those galaxies and just work through that and add up all the light coming from that and work on the basis that on average all the stars in those galaxies are about the same luminosity of the sun. This is not true, obviously. There's some much brighter, but there's also quite a lot very dimmer. So it works out not to be too far off that point. So by just calculating how much light was coming from the cluster, he managed to come to a figure of how much weight was there, and it was about 1 trillion solar masses, 10 to the 12 solar masses. So that's a nice estimate. But you can also do it by looking at the motion of the galaxies around each other. They have to be held in place. And you can use the virial theorem for that. And he did that too, and he came up with a figure of 10 to the 14. So this is 100 times more mass present in this cluster, worked out by how they're moving compared to how much he could see. So he said at the time, and coined the phrase, in fact, there's a lot of more dark matter in this cluster that I cannot see that is holding it together. So obviously you can only see the bright, shiny stuff because that's giving off light. Anything that's dark in there, you just can't see with the telescope. So that was one of the first indications. It was kind of an interesting sort of sidebar, but not particularly taken up. The next big step was looking at orbits of galaxies. And if we just take our solar system, we can see one of these velocity curves here that Mercury, being very, very close to the sun, has to whip round really, really quickly in 88 days or so. If it was going much slower, it would get pulled into the sun, whereas Pluto, long, long way out, taking 238 years or something like that, can really go round very, very slowly because the effects of gravity at that distance are really quite small. The solar system is pretty easy to analyze because most of the mass is really in the center or in the sun, and all the rest is just sort of fluff around the edges. So it's a very easy calculation to do. But you can do the same with a galaxy, and particularly is M33 looking at this. It's a little harder to do because not all the mass is in the center, but nevertheless you can sort of estimate how much mass is at each ring and work out through the theory. And when this was done, they observed the very top line with these yellow error bars. But the theory from Kepler and how gravity works says, no, this should be what's happening, because you can clearly see there's less and less stars as you move further and further out. So the speed of the stars should really decrease quite quickly. So that was noticed, particularly Horace Babcock in 1939 had a thesis on it, but the results were somewhat ambiguous at the time. But Vera Rubin came back in the 1970s and had much better equipment, could also use now radio astronomy to look at clouds of gas. So she could extend the results much, much further out from the visible stars and track clouds of hydrogen that were also orbiting around, and say, no, this disparity between what's predicted and what's observed is quite huge. And well, we could fix it by having a lot more mass sort of surrounding the galaxy, and in fact about 5 times as much mass as we can see. So that's kind of when it got real. Not too long after, there's another element of evidence that came to appear, which was Big Bang nucleosynthesis. So this is what happens really early on in the universe. And Fred Hoyle here did quite a lot of work on this. So if you take the Big Bang and you start off with a very, very, very hot universe that's very, very compact, and then it starts expanding very soon after that, and grows to the size we see it now. But if you follow that track along, at a certain point, and it happens about 3 minutes after the Big Bang, the universe is really, really hot and equivalent to being inside a large star at that point. And when you're at that heat, and you have enough density, you can get these nuclear reactions that happen. You can get protons colliding with protons and neutrons to form deuterium, tritium, helium, and other elements like that. But it's very sensitive to how much of the density of the universe is in atoms. And doing that and then comparing to observations, you get this sort of chart, which is a bit busy, but this blue bar is kind of where we get our observational constraints from. And it says it's somewhere between 3.8 and nearly 5% of the universe is made up of this stuff called atoms to actually get to this basis. So this is something quite outside looking at rotating galaxies. Yet another one which I've not done any work on, but I use extensively, is that if you try and do simulations, you can put into a computer a model of the universe and let it run and see what it turns up with. If you just put in regular matter and let it run of the amount we suspect was in the universe, you don't get at today's time anything that looks like our universe today. You get something quite different. If you put in this dark matter at different amounts, then you do get closer and closer to the universe you see. And indeed, if you put in about 5 lots of dark matter to every one of regular matter, you get a much, much better prediction of the universe as we see it today compared to what you do without. And some of that is because when it's really, really hot, all that atoms and whatever are interacting with the bright luminosity of the early Big Bang and all this very hot stuff. Dark matter doesn't interact with light, so it gets on and settles down to form the seeds of galaxies a long, long time before the atoms can sort of stop being excited and settle down and start forming stars and galaxies. So that was another sort of leg to stand on. Another one is gravitational lensing. Einstein predicted that very large masses will bend light, and we know that's true now. We've done experiments on that, and indeed we see these out in space, and we have very good constraints on this, and we know exactly the equations you need to run to get this to work. Well, I'll show you one here. This is the foreground galaxy, which is an elliptical galaxy here, and there's a galaxy way, way behind this blue one that you're just seeing bent around it. So it's quite distorted, but you can see all that. But we know kind of how much mass is in this elliptical galaxy, or a good estimate, and it's not enough to bend the light as much as we're seeing it. So it needs a lot more matter within that to bend the light to the amount we're seeing it. It also happens with galaxy clusters. So this is a nice cluster here, but you can again see these streaks. It's not nearly as nice an image because you've got quite a lot of matter spread around that's bending the light in different ways. And our best constraints really come from the cosmic microwave background, which is this residual energy comes out in microwaves that appears to be all across the sky. And by doing some very clever calculations, which are beyond me, you can actually work out some of these properties. Normally they look at this map and say, well, if you look at this, you can see there's a certain scale to this. There aren't huge areas of red or huge areas of blue. They all have a certain size. And when you look at that on this sort of map here, you can see actually here, this is the angular scale that map was showing. Most of the little dots there were about 1 to 2 degrees on the sky. And this is, so the green is the prediction from theory, and the red are the dots from observations. So it's a very good theory fit. But what this tells you, these number of bumps in this curve are kind of interesting. The first one tells you the geometry of space, that it's kind of flat, at least as far as we know it, it seems very, very flat, which means if you set off in one direction, you will never come back to the position you started on. You could do that in certain models, like if you walk around the Earth, if you set off in one direction and keep going that way and walk across water and everything, you'll end up back where you started with, because Earth is curved. Space could have been curved, but it now appears to be flat, at least to a very good degree. These second two peaks, though, here and here, they tell you what ratio of regular matter, the baryonic matter, is to dark matter. And again, it comes out about 5-to-1 dark matter to baryonic matter. So this evidence, and there are other more obscure forms of evidence, all lead us to think there is something missing, which is this dark matter. So our best view is that a galaxy like this is contained within a dark matter halo, and the dark matter halo is about 10 times as big as the galaxy. So it's quite extensive, and this is what gives the rotational velocities the right thing. So if you were looking out at night, so here's the full moon, this is Andromeda, if you could see it you know, in all its glory rather than just the very core. If you could see the dark matter halo contained in that, you could see quite an extensive area was covered by that. Unfortunately, we can't see dark matter, but it could well be there, and at least it lets you get this joke about you know, maybe saints have a huge dark matter halo as a regular halo. And a very nice animation, which or simulation, which I've never been able to track down who did it, shows this. This is a spiral galaxy rotating, and at 500 million years, the dark matter is just removed, and you can see what happens. Only the stuff right in the center stays bound to this galaxy. All the rest goes flying out because there isn't enough gravity there to hold it. And as it says there, do not try this at home. This is not a safe experiment, so please don't try that. So I mentioned briefly about hot dark matter. So this would be something that moves at very high speeds, the same speed of light. And it's upsetting, really, that this doesn't exist, because neutrinos would have been a great solution to this. But it does not give the sort of universe that we see. So we now believe it's cold dark matter, that small clumps grow and they merge together and grow bigger and bigger over time, which is almost the opposite of how hot dark matter would exist. However, there are one or two issues with this, which is why we're not really sure whether it's cold. So this is a simulation of a Milky Way-like environment done in Durham, just looking at the dark matter. You could see the Milky Way would be in this very central bit, but you can see around it lots and lots of little clumps of dark matter. And these are called the satellite galaxies. And the prediction from simulations is there should be about 3,000 of these satellite galaxies orbiting around the Milky Way. At our best, there's maybe 100 to 150, most of them really tiny. So this is called the missing satellites problem. And one solution to it, not the only one, is you could have slightly warmer dark matter than cold dark matter. So this is a warm dark matter simulation where you heat up the dark matter somewhat, and you get a much better picture of something like the Milky Way environment. It does also bring with it quite a number of other issues, so it's not a solution all on its own. But you may occasionally hear of warm dark matter, tepid dark matter, lukewarm dark matter. These are all phrases that are bandied around. So with that, what could it be? What have we got left in our bag of bits and pieces from the universe that it could possibly be? Well, actually, there are two ways to fix it. The first one is to say, well, gravity doesn't work like we understand it, that the equations of Newton, as enhanced by Einstein, are actually not the whole story, and there are more things that we need to understand about that. This is certainly a possibility, but gravity has been so heavily studied over the past 100 years or so that it's really quite difficult to squeeze something extra into the equation, because, you know, we've used this theory to get to the moon, we've used it to get to Pluto, other planets, and it works really solidly and, you know, very, very well in laboratory conditions too. So we tend to go with the second one. There's a whole load of missing mass that we can't see. Anything dark is very difficult to see. So that's kind of where we go with. And the shopping list is it must be stable. We really need it at the very beginning of the universe. So it can't sort of decay over time. So it needs to be that. It has to be electrically neutral. It has to influence gravity because that's how we're seeing it. So, you know, it can't be completely invisible. Yeah, not interact with light, which is kind of the same as the second one. So obviously we start off with things that we understand, and these are usually lumped together under the name of machos, which stands for massive compact halo objects. So these are things that are existing things that we know about. So one of these is neutron stars. Neutron stars are very tiny, you know, like 10 kilometers across. They're very, very difficult to see unless they're also pulsars, which sort of have them signaling to us. So neutron stars, maybe there's loads and loads of neutron stars that we can't see. Black holes, I mean, they are black. So there's lots and lots of black holes floating around in the galaxy and around it, that might well be a possibility. Could be extra gas. There could be lots and lots of hydrogen lurking around that we've just not noticed. Or brown dwarfs. These are things that are smaller than stars and bigger than planets, so somewhere on the cusp of those two. Sometimes some theories produce lots and lots of these brown dwarfs when you form planetary systems. So those are all possibilities, but by and large they've been ruled out by this technique called microlensing. This has also been used to find planets around other stars, which is kind of where this graphic comes from. So this happens by, if you look at a very distant star and something comes between you and it acts as one of these gravitational lenses. And if you follow the light from it, which is along the top, you see it gradually gets stronger. Then you get a blip, as in this case, a planet, then another blip as the star goes across. So this is a technique. It's been used to find a number of exoplanets, but you can also use it to test out this theory. If you look out of the galaxy, you should see quite a lot of these objects pass between you and very distant objects like quasars or other galaxies, and they would brighten up. They would lens them as they pass. So it's a bit of a hit and miss thing because you've just got to look and hope something passes between you and another bright object. But people have done these surveys. They have indeed found these things that are passing between distant light sources and ourselves. But you need a lot of these to fulfill the amount of missing mass. You need 5 times as much of this stuff as there is in the Milky Way. So this should be happening pretty rapidly, and they've only found a very few of these, so nowhere near enough to sort this problem out. So by and large, machos are sort of dismissed. So what else have we got left? Well, we've got to kind of invent stuff at this point. So the other possibilities are things called WIMPs. So this was really nice. We had machos, and now we have WIMPs. So these are weakly interactive massive particles, of which the neutralino used to be the very favorite one. There's also other ones, the stereoneutrino, the axion, and then we get more bizarre, well, gravitons. There's a whole dark sector. There's recently some discussion of dark photons and things like that. So that's a whole dark sector. And then things that I really don't know much about. So there's the macros and cue balls, fuzzy dark matter, wimpzillas, and things like that have all been proposed. They all have papers written about them. They are possibilities. And they all lie on this rather extensive chart. So this is where stuff lies, and along the bottom is the mass scale, so how heavy is the particle, and up the side is how likely is it that you're going to be able to detect it. This is kind of cross-section, but really it comes down to how easy is it to detect. It's a huge scale. So up here we have the electron and the proton in red. So those are pretty easy to detect. I can clap my hands and they don't pass through each other. That's pretty easy to detect. Neutrinos are right down here, so they're much lighter than electrons, and also, thousands of times more difficult to detect. They have a very tiny cross section. Pretty much everything else is really tiny below that. So the WIMPs are down here, the axions are over here, WIMPzillas, whatever they are over here. And there's even something called fuzzy cold dark matter, which is tiny, tiny, tiny masses. I mean, down here somewhere at 10 to the -6 or so is where the electron is. And this goes down in jumps of 1,000 times smaller, 1,000 times smaller. So by the time you get over here, it's ridiculous. And likewise, going up this way, these are black holes up here. So there is a theory of black hole remnants that could still be possible. It's kind of on its last gasp as a theory, but that's the range we're dealing with here. So let's look at a few of these. Let's start with the WIMP, the neutralino, which used to be the very top contender for all this. So this comes from a theory called supersymmetry. So these are all the most primitive particles there are. These are quarks. They make up neutrons and protons. We have the electron down here with its partners, and also the force carriers like the photon, the gluon, and the Higgs particle here. They came up with a theory and said, actually, I don't know the maths bit, but it's basically if all these particles had an equivalent that was sort of symmetric, this is not anti-particles, but completely different particles, then suddenly the maths would be a lot easier to work out, and we could work out why certain things were happening. So this is where supersymmetry came from. So originally this was the standard model that, well, this is still the standard model that we work with. Not me, this is far too complex for me. But it said, well, if we have this supersymmetry and each one of these particles has an equivalent supersymmetric particle, then suddenly lots of things become a lot easier to solve. So this came out with this supersymmetry thing, and we have these things here called supersymmetric quarks or squarks for short. We have selectrons and neutrinos. They all get an S on the front of them, except for the bosons, which get enos on the end. So we have the photino, the gluino, the xeno, and the wino, and the Higgsino. So if this was the case, then you can actually make particles out of that, and in particular, you can make the neutralino out of some combination of these, and this would be the lightest supersymmetric particle that was stable. And there could be loads and loads of these, and this would be wonderful. It would solve two problems in one. It would keep the theorists happy that they had a much better theory of how everything worked, and we'd also have a dark matter particle. Slight issue with this is there is no evidence for either of these things being the case. So that's a bit of a shame. We've not stopped looking for them, but so far this was going to be one of the great hopes, and it's not been found. So another one was called the axion, was named after a US washing powder called Axion here, the grease scrubber, and it was proposed in 1977 by Pecky and Quinn, and they said we kind of need this to sort out some of the really deep details of how atoms hold together, so-called quantum chromodynamics. So they made up this particle called the axion and said this would really help solve everything. It could sort out a few equations. And incidentally, later on, they said, well, this could also be a really good dark matter particle. So we'll have one of those. Again, great theory. No evidence that it actually exists. Been a couple of papers that thought maybe they'd detected it, but those have long since been sort of squashed, and people are still searching for it. So the axion, not quite there. It's probably one of the better candidates nowadays, now the neutralino has not been found. Another one is called the neutrino. So we have these neutrinos. We have the electron neutrino, the mu neutrino, and the tau neutrino. They all exist, and we know somewhat about them. But the interesting thing is they all have a left-handed property, and they have a very, very tiny mass. But every other particle we looked at seems to have a left and a right-handed version. So it's kind of interesting to speculate. Well, maybe we've missed out and not found a right-handed version of the neutrino. And maybe this has a small mass, and if there's plenty of them, if it has a bigger mass than some things, then this would stop it moving at the speed of light, and it could drift around, and it could be a very good candidate for dark matter. So this is called the sterile neutrino, and I'm still hoping this will turn out. A few years ago, an experiment called Microboon in Chicago said, no, we've ruled that out. And I thought, oh, well, that's the end of my dream. This will be the one to sort it out. But then IceCube in Antarctica said, no, the evidence is not quite that obvious, and it could still exist. So IceCube has ruled it back in as a possibility. Still no evidence that it actually exists, but it's what you can hope for. Then we get to more weird and wonderful things. So string theory has these extra dimensions, and it has extra particles associated with these, and these can move in and out of dimensions. They're called Kaluza-Klein particles after two people who came up, not with string theory, but with the idea of extra dimensions sort of thing. So the KK photon and the KK neutrino could both be possibilities of that. This is my complete summary of string theory, and it's kind of the state of the art at the moment, that there is no practical evidence that string theory is correct. It is just a mathematical formula. We don't even have a way of working out how to do an experiment to prove it at the moment. It's so far beyond our abilities that it's really just a mathematical thing at this point. So, yeah, we've still got possibilities here. The other ones I'm not going to talk about because I don't really know much about them. The Wimpzilla, cue ball, scalar graviton, magic unicorn dust. Okay, that's mine. I threw that one in, but I think it's got as good a chance as any of the others, except there's no paper written on it. So this is where we find ourselves. We're looking for dark matter. We're sitting in the middle here, and we have all these theories floating around the edge, all jostling for position to be the dark matter particle. And there's just many possibilities. It's not that we don't know what it is. It's just that we have too many possibilities really at this part. So it's pretty difficult to make too much progress on it at the moment. Just as a side, how much dark matter should there be? It depends quite a lot on how heavy it is. But if it's a 5 gigaelectron volt particle, then a standard Coke bottle, or Pepsi bottle in this case, should hold about 120 particles. So there should be plenty of them floating around in the room you're sitting in. If it's heavier, then you're probably only at 10 particles per Coke bottle. So that's kind of the range that we're sitting in. Third part, okay. Well, how can we go about detecting it? We can detect it gravitationally, but that's not very not very enlightening. It just means there's something there that we can't really see. So there are three ways. The first is to make it, and this way you use a particle collider. You collide things together at huge energies, E equals mc squared. You put enough energy in, you perhaps get mass out, and you may get the new forms of mass. So a Large Hadron Collider is the best possibility of that. You send particles shooting around and collide and see if some of it pops out as dark matter. If it does, there is an issue there in that you can't detect it because dark matter doesn't interact with anything, so it would just disappear out. But particle physicists are long used to that. They know how much energy goes into the collision. They can count how much energy comes out. And if there's a huge amount missing, then that shows that you've produced something that you can't detect and it's escaped from the collider. So far, this has not shown up anything along those lines. So dark matter is still hiding from this. Two possibilities: it doesn't exist, or we just haven't got enough energy in the Large Hadron Collider to generate it. So those are two possibilities, I guess there's some other theoretical possibilities. This has also ruled out some of the models of supersymmetry. So the supersymmetry that would have given us the neutralino, the Large Hadron Collider said not at the moment. There are thousands of different supersymmetry models though, but it's ruled out the kind of most simple ones. So if we can't make it, perhaps we can try detecting it. It worked for the neutrino eventually, so we could try that again. And this is very much like looking for neutrinos. You don't want to look for them on the surface of the Earth because there's too much noise going on there. You get cosmic rays coming in a lot of the time, you get other disturbances. So most of these detectors, and indeed neutrino detectors, often go deep underground. They use old mine shafts or sometimes existing working mines, and they bury their detectors deep down in the rocks, because at least there you get rid of quite a lot of the cosmic rays. You have other problems that the rocks are radioactive, so that occasionally triggers false positives. But it's a lot better to work deep underground than not. So there's mines like this where you go down a kilometre or two and get into special clothing that is extremely sterilized and doesn't have any radioactive particles on it, etc. And build a detector, and you can build them out of various things. This is one built out of liquid xenon. So it's a big container of xenon. It's just sitting there. It's shielded from all sorts of other things, so you don't get spurious detections. And what you're looking for is a dark matter particle to come in and strike one of these atomic nuclei. Most of the time they won't. They'll go straight through and not worry anything. But once in a long time, and depends how big your detector is, but it could be like once every month, there is a chance this might happen. And in which case you've got something sensitive enough, the xenon atom will then go flying across, knock out some electrons, and you get a small electric charge, maybe a flash of light, something you could detect. But at the same time, you get lots and lots of other things going off. You still get the odd cosmic ray coming through, you get the odd neutron coming in from the rocks, you get other bits and pieces. So you've got to kind of shield from as much of that as you can, and then account for most of these other ones and see if you can filter out all the good ones and the bad ones. And say you're looking for about one event a month or two, something like that. So it's a very, very slow, laborious process. And this is the state of the art in these detectors. This is a really noisy figure, but these lines are the very different experiments. So here's COOP 2012 at the top, and this blue line for COOP 2012 says this is the limit of our detector. The blue line is kind of where we stop. Everything above that blue line means if the dark matter existed in that region, we would have found it with this experiment. So you get bigger and bigger experiments. There's xenon 100 here. I think that was 100 kilograms of xenon. There's xenon 1 ton down here. So they get bigger and bigger and more expensive. But you can push the levels down and try and detect where it is. It's probably somewhat of a thankless task at this point, in that they produce papers every year and say, guess what, we haven't found anything, but we know it's not over here. So as I say, it's a bit like looking for a dark black cat in a coal cellar with no torch, and you're not even sure if the cat's there. You can say, well, we've ruled out, this tiny corner of the cellar. We've poked around there and it wasn't there. It could still be somewhere else. So that's kind of where you are with that. So that's looking for things like the neutralinos and the WIMPs, the relatively massive particles. For axions, they're much harder to detect because they have much smaller cross-section, but they do have a fatal flaw in that they can couple with very strong magnetic fields to photons, apparently. So basically you're looking for stuff that comes in as axions, goes through a powerful magnetic field, and then appears as photons. So you're looking for brief flashes of light that come through this sort of detector. So far, again, they haven't found any, but they're still looking. So that's the second way of trying to find it, and there are other experiments for both of these. The third way is to look where the concentration of dark matter might be at its biggest, which would be kind of the center of the galaxy, because that's where everything is crowded together. And most of the theories seem to suggest that dark matter is its own antiparticle. So you will occasionally get a dark matter particle meet up with its own kind and crash into it. Very, very rare event. But if it does, you'll get a burst of energy, which will probably come out as something like a gamma ray or an X-ray. We've looked hard. There hasn't been anything that you can't explain by other astrophysical processes. So that's the third way, and hasn't really worked. So at this point, it's getting a little desperate, as you could probably tell. People have started to go back and look at other possibilities. So the one possibility I mentioned earlier was maybe the theory of gravity is wrong. So that is another alternative, and one that's been pursued by certain researchers for a considerable number of years. So let's just have a very quick look at the alternatives. So the favorite is one done by Mordecai Milgrom, who came up with MOND, modified Newtonian dynamics. And in this case, he takes the second most famous equation of all physics, F equals ma, and he tweaks it a bit. Say it's F equals m, some function of a times a, and this a naught constant in it. If you follow the maths through and you put in suitable values for this a naught, which is an acceleration term, you can change from the force of gravity here that we understand that Isaac Newton came up with to a different force of gravity that looks like this. So it's a very different formula, but that's what happens if you follow it through. But crucially, if you then again look at orbital velocities, this is the orbital velocity here, v squared is equal to g and the mass, but over r. So as you go further out, the velocity should change. In Milgrom's form, there is no r in the equation, so velocities should be constant, which is exactly what we see in spiral galaxies. So it's very attractive from that point of view. It does have a few issues with it, though. I mean, get the pros first. The galaxies behave perfectly if you put his equation in. It also gives some well-known relationships. If you've heard of Tully-Fisher relationship for galaxies, that explains that. And it also reduces the number of dwarf galaxies around Milky Way, which is also good. Some things it doesn't work for. You can't explain cluster dynamics or the cosmic microwave background with MOND. It doesn't work for that. Secondly, we know gravity works how it works on Earth. And what he's basically saying is, no, it doesn't work like that in really, really big scales. So gravity has to change its behavior from how it works in the solar system to how it works for gravity. So it must have to sort of morph itself as it changes. And it also doesn't work for, if you put relativity in it, it doesn't work at all for that. Birkenstein, though, had a go at fixing the last one. He came up with a relativistic version of MOND called Tebes, which does work. He had to work really, really hard to get that. It took him a number of years to get all that to work. There are some question marks over that. Some people have suggested maybe stars would be unstable if we were working under the laws of Tebes. So there's a whole lot of other theories, forms of gravity, FFR theories, where you modify Einstein's theory. But I say it's a really difficult thing to do and keep gravity working as we know it does. Just one interesting one I've seen recently. There's been lots and lots of ways to try and solve this. This was Justin Curry said, well, maybe it's a bit like a phase transition. So I'm sure you all know water can exist as ice, solid, liquid, or a gas as steam. And there's very solid boundaries between those. It's 0 degrees. It will change from ice to water once you get above that. So the idea is maybe this is like a superfluid, and when it's behaving in one form, it gives you like the MOND type theory of gravity. and then you go above a transition, which might be mass or gravity or something like that, and suddenly it will flip and change into like water and behave rather differently. And a superfluid seems to match this quite well. So this was only proposed in 2015. Sabine Hossenfelder, if you follow her YouTube channel, she talks about that as a possibility. But so far, there hasn't been any evidence for this, and people working in the area basically have got enough experiments to run that nobody has quite thought of an experiment to test this. So that's kind of all we know about dark matter. So I hope you'll leave this talk thoroughly confused, but at least understand all the issues that we're worried about. So just to sum up, cold dark matter, is it cold? It probably is, in that it's not moving terribly fast, but you know, it could still be warm. Might be warm dark matter that we're looking at. Dark is not a good name for it really, because it doesn't matter how much light you shine on it, you'll never see it. Transparent is a better name. And is it matter? Well, if we kind of knew what it was, we'd be able to answer that. So, you know, it could be huge black holes, or it could be tiny, tiny fuzzy things. So until we get to the bottom of that, I don't think we really know. But I'd like to leave you with this, what I think is probably a good answer. And thank you very much for your attention.
Thanks very much, Julian. That was excellent. Thank you very much. Can we unmute and thank Julian for his presentation, please?
Thank you.
And questions, please? Can we have questions in the chat or directly, whatever?
I think Nigel's got a question.
Yeah, if I could ask a question. Thank you, Julian. That was absolutely fascinating. Given the new instrumentation that we're developing, both Earth-based and space-based, what sort of progress do you see us making in this field in the next 10 years or so?
Well, some of the new telescopes, particularly Euclid, are really good at mapping out where dark matter is. That's in fact one of the sort of science goals of Euclid, and quite a lot of it's been doing at Edinburgh with the Astronomer Royal for Scotland as one of the leaders in that. So that will help us map out where the dark matter is and give us some good constraints on it. But for me, it's not quite as satisfying. I'd really love to know exactly what it was, rather than just where it is. So I would find that more useful, just as a curiosity sort of thing. So you can do a lot with where it is. There are some other things you can do on. I was at a talk yesterday, in fact, where they were looking at again some Euclid results, but you can look at whether dark matter is self-interacting. It interacts with itself or it ignores itself. You can get some constraints on that from looking at clusters of galaxies and the matter within it. So again, it's pretty hard to do, but you know, most of the easy questions have been asked now. So I guess these are still the hard ones. But yeah, some of the new instrumentation is really going to help sort of pin down where it is, and maybe that will show up stuff that leads us forwards.
That's great. Thank you.
Jim Barron, you have a question? Do you want to answer it? Ask it?
Yeah, thanks for the talk. There is an issue with supermassive black hole growth. Some of the big ones seem to be much bigger than can be explained.
Yes.
But would the Eddington limit, the radiation pressure that stops them growing, be a factor at all for cold dark matter, or could CDM just pour into black holes unaffected?
Yeah, that's a really good question, and a very good thought. There's kind of how can I best describe this? So you kind of win and you lose with dark matter. So if the dark matter is heading straight for the black hole, it will go in no problems with that, from all we understand anyway. But it's not very good. It's not as good as regular matter. Regular matter can be sort of be funneled. It can be, do sort of like swirling disks that slow down by friction and then pour into the black hole and up to, as you say, the Eddington limit. So a black hole can sort of suck in stuff from quite a long way away because it eventually loses angular momentum and ends up in the black hole. Dark matter, because it doesn't really interact in those ways, it can't shed energy in quite the same way as matter can, where it can radiate it away. So yeah, I mean, it would take all the dark matter that you throw at it, but it's rather difficult to gather it up from extensive areas around it. So, you win some, you lose some with dark matter.
Okay, thank you.
And Julian, if you had to put your money on it, what do you put your money on?
At the moment, well, I don't have any better clue than the rest of you, or probably worse in some cases. But yeah, I used to have my money on the neutralino because that seemed like it was solving so many useful problems all at once. But the evidence seems to be against that at the moment. One of our researchers at Nottingham did a lot of work on axions and still does, and thinks that's the way to go. I've got this soft spot with no theory or anything else behind it that maybe the sterile neutrino is the answer, but I just kind of like that, just with no reason to particularly, just I like that answer. So I wouldn't put any money on any of them.
Okay. Will, is there any questions on YouTube?
No, a fantastic talk. It's good response on YouTube. There was one. I think really it's a very difficult question how the best way to search for it, if you see what I mean. You're just looking at every angle and these, as you say, the sterile neutrinos and stuff like that. But from my side, what would be, do you see any technological breakthroughs possibly that could come to try and actually detect it? If you say there's 10 particles in a sort of bottle in your room, something like that, do you perceive that there could be a possibility for a technological breakthrough to actually detect it, or do you think that's completely out of the question?
I think in the absence of anything new in physics, I think it's going to be a really hard thing to do. I mean, we sort of had the same problem with neutrinos that, Pauli said, you're never going to detect these. So when Ray Davis first detected them, I think he detected 10 in a day or a week or something like that. So it was tiny, tiny numbers, and we've got better at it. But even today, it's like, I don't know, the best neutrino detectors in the world detect a handful, 20 or 30 a day or something like that. And there's billions and billions coming across.
Absolutely.
So it's just the fact they really don't want to interact with anything that means you can't detect them. And dark matter appears to be, that, but many times worse. So
Excellent.
without some
Thank you.
sort of theoretical breakthrough or something like that, I think we're just going to struggle for a while.
Excellent. Thank you.
Thank you very much. Any last question, everybody? I think you've done your job in confusing everybody.
Well, that was my goal. Thank you very much.
Well, thanks very much. Thanks for coming on and giving us such an intriguing talk. Thanks.
You're very welcome. Thank you.
Thank you again.